Hi guys, you probably expected to hear Mr. Andersen, but today we're going to try something different. So Mr. Andersen's video that you're going to be watching as I speak over it relates to bioenergetics. And bioenergetics is how biological systems use free energy. The plant in the middle is called Arabidopsis. It's a cute little plant used for a lot of research. And then to the right of that thing is that ugly, monstrous looking, complex diagram, and it shows the metabolism of just the Krebs cycle in Arabidopsis. And this is how it's converting acetyl CoA into carbon dioxide and making NAD and FAD. This is very complex, as you can see. Each of the red dots represents an enzyme. Each of the lines represents chemicals moving between those enzymes. But you need to know the basis of bioenergetics, and I'm going to help you with this. Life requires free energy or available energy. In other words, right now, as you sit here, as you think, your ATP is being used by your brain in order for you to think. If you don't do that, you'll end up dead. So death is the opposite of using free energy. There are two laws of thermodynamics. The first one you're probably familiar with. It's basically something like conservation of energy. In other words, energy is converted from sun to plant to bread to ATP to ADP, and your brain is using that energy. And the total amount of energy in a closed system will always be constant. We cannot create or destroy energy at each of the steps. We simply convert it. All energy will end up eventually as the lowest form of energy, which will be heat. Manny, pay attention, Manny. People are not confused by that usually, but sometimes are confused by the second law of thermodynamics. And what basically that is that as we move through time, with each chemical reaction, we're increasing the entropy, or the randomness disorders. In other words, with each chemical reaction, from the sun to the ATP in the brain, we're losing order. It's becoming more disorganized. So evolution seems to point the other way, which is over time we're making things more and more complex. And people say that we're violating the second law of thermodynamics, and that would be true if evolution happened all over the universe. But remember, we're just a little tiny dot. We can increase order in one area by decreasing order in another area somewhere else in the universe. So that's basically the second law of thermodynamics. Next we come to the idea of Gibbs free energy. And some people get confused. So we're going to go nice and slow here. Here's the cartoon method of it. This is the equation that confuses some people. You have this delta G, which is change in free energy. Melissa! H is the total energy, T is the temperature, and S is entropy. So the first thing that you need to think about is that free energy is the same thing as available energy. Flores and Schubert, pay attention. Moscoso, stop being so loud. So we're going to go three spontaneous reactions so that you can see reactions that occur on their own without any additional input. And we're going to look at those values. So here's the H. Ball, top of the slide, here's the first one. It's got more energy than at the bottom, right? Clearly, because it's got more potential energy. Total, stop bothering Velasquez. The potential to actually move down. So it took some energy to bring it up there. So as it goes down, the H value will go down in a spontaneous reaction. Let's look at the next example now. Now we have a bunch of molecules in a closed container, and think of it as a gas container, because they're moving around like Mr. Andersen's hands, moving around. And if we move one of the walls, since they're more space and they're going to be randomly moving, they're going to cover the whole area by itself, and that will increase the entropy, and therefore the randomness is becoming greater. If we remove the whole container, the whole thing will go all over the place, and S will increase. In a spontaneous reaction, the amount of entropy will always increase. Now let's look at temperature, which is the last variable. So is that going to spontaneously explode? No. But if we increase the temperature, it will explode. We'll have a spontaneous reaction. It's cartoon, but it gives you the idea. So let's look at the whole thing in summary here. Action delta G went down in the first one. Joel, what it should do is the G should also decrease. If the molecules increase, well, we increase the S. Well, what else could increase it? You can also increase the temperature. So the last two did that. So mathematically, if you increase those two values and you're subtracting it from the total energy, so what will happen to a delta G? The delta G will be negative. Here's a summary real quick. If you have a delta G, so delta is change. If it's less than 0, that's spontaneous. If delta G is greater than 0 or positive, it will be spontaneous in the backwards direction. It's a non-spontaneous. It's called exergonic when it gives off energy. And the second one will be endorgonic reaction, when it takes in energy. Delta G and change is equal 0, you will have equilibrium. Well, that looks a lot like physics, but we haven't talked about bio, so let's get to the bio right here. You have a molecule of glucose in the presence of oxygen. Remember, you need oxygen in order to make it burn. Well, will that release energy, or will it take energy? Well, it'll be exergonic. It will release energy. It will release the energy between the bonds, and it will move away from glucose and oxygen to carbon dioxide and water. And you will see the delta G there is negative 686 kilocalories per mole. So what it means is that if you have a mole of glucose, you're going to release that number, 686 kilocal per mole. That's the change in G. The change of free energy will be negative. So the energy, as you know, was in the hydrogen in there. Bonds have a lot of energy. All the hydrogen grabs onto the oxygen, and it will lose that energy. It will be released. So let's look at an energy diagram right here. And the glucose and oxygen have a certain amount of free energy at the beginning. John Paul, when it is done, they have less energy. So if you were to draw the energy diagram, you would go up in energy and then go down. That's what an exergonic reaction or energy releasing reaction looks like. If you know what chemistry at all, you know that this is called the energy of activation, or the activation energy. In that sugar in the table doesn't just spontaneously break into, release that energy. You have to put some energy into it, and then once you get that energy, you loosen the bonds, and then it spontaneously will break down. Vargas and Tubman, come on, stay with me. So you need that net change. You had more at the beginning, and then you have less at the end. Hernandez and Morales, let's go. Are you getting this? So that change, you see the decrease. And delta G, it will be less than 0, which means it's negative, and it's exergonic. It gave away energy. Rodriguez, use cellular respiration to make sure you convert some of that ATP to ADP. Let's get this stuff, okay? If you look at the next one, look at photosynthesis here. Well, so it's the same thing, but in reverse. We have carbon dioxide and water, and you make glucose and release oxygen. So now the positive value of G is endorgonic. It took energy. And if you look at it, here's the diagram for that one. You will see you start less energy at the beginning with water and carbon dioxide, and then at the end you have higher energy. So you see that you have that activation energy still, but if you look at the overall delta G, it's going from negative or greater, lesser to greater. So now it's greater than 0, so it's endorgonic because it requires energy. So where does it come from? And the planet comes from the light of the sun. The light is what's going to be given that energy to take and create that higher energy at the end. They're doing that in order to do cellular respiration and release that energy back in the mitochondria in the form of ATP. They're not making the sugar for us. They're making it for themselves so they can store it, and then you can use it using cellular respiration and then produce energy, of course, in the form of ATP. Speaking of which, this is ATP. Here are the 3 phosphates. Here's the last phosphate right there. It becomes unattached, and there's ADP, and there's a phosphate, and the negative number of G is a lot less than cellular respiration. It's a smaller molecule, but you have released it. If you want to make ATP out of ADP, now you have to have a positive. So if you break the phosphate, negative. If you formed it, positive. So constantly changing back and forth in our body as we move any part of our body, you'll break that ATP to ADP to provide energy and then provide it again through cellular respiration, putting it back together. So what's important when we talk about bioenergetics? There's 2 chemical reactions or chemical processes that take place. Photosynthesis is the first one, and it happens in the autotrophs, and anybody who's for autotrophs making energy out of light, you're going to take that energy and you're going to make glucose. And then the second thing is they're taking that glucose through glycolysis, Krebs cycle, electron transport chain, and releasing that in the form of ATP. I hope that makes some sense, and this is the beginning of something that I hope to do more often for you guys. Remember, the reactants of one and the products of the other are the same, and the delta G therefore will be negative in cellular respiration and positive in photosynthesis. And I hope that helps.